Okay, so it has started recording. Welcome back after the weekend. And as I was just telling you before I started recording, this is the last week of the lectures. So our course is coming to an end. And so today we will have a lecture, this lecture, and tomorrow we will have a lecture, and tomorrow's will be the last lecture of the course. Okay. And as I told you, we have an hour on Thursday, which we will convert to so-called office hours. In the sense, if you have questions, you can come and ask me. I will make myself available on Thursday, 11:35, our usual time. Okay. All right. So I should start sharing the screen. So let me start sharing the screen, and as usual, one of you please confirm that you can see the screen.
Yes, sir.
Yes, sir.
Excellent. So this beautiful topic of Laplace transforms, I think I'm covering the theory part today anyway. And of course, it's not about theory, it's about practicing solving a lot of problems. So I will discuss maybe a few more problems tomorrow. Okay. I don't think there will be anything new theory-wise tomorrow, and tomorrow will be the last lecture. So let's continue. So what we have, so I have made the usual mistake. So give me a second. Let me just remove the pauses. Okay. Maybe I can do it in front of you. Uh, can you see the text file?
Yes, sir.
Okay. So, and you know what I should do? No, one of you can tell me what I should do in order to remove the pauses. I told you this once long back. Okay, maybe you don't remember, or
Sir,
maybe
we can't see the text file.
you can't see the text file. Okay, anyway, let's not spend time. So maybe at the end of the class, but you should be able to see, no? So let me share once again. Okay, okay. Now you can see.
Yes, sir.
Yes, sir.
So here, there was a handout. This is how it was. And if you compile, it comes like this, and see, the whole thing is, okay. So
Now we can't see that.
I have opened a wrong file. Okay, anyway, I just have to remove the handout here. So since anyway I was sharing, I will share once again. I hope there's enough time. Can you see the text file? You can see the text file,
Yes, sir.
and
Yes, sir.
you can see the PDF file.
No, sir.
Okay, so there is a problem with sharing. Maybe I should have shared the desktop. Okay, so anyway, quickly let's do that. So if I share the desktop, what do you see now?
Cool.
Both.
You can see the text file, and when I compile, you can see the PDF file, right?
Yes, sir.
And in the PDF file, see, I mean, the full thing is coming. No, it's not coming with pauses. So that's what I wanted to remove. And what I go is at the start, and you can read handout there that I need to delete. Okay, and then compile. And now it should come with all the pauses. So this is what I usually do just before the lecture, but today I didn't do that. Okay, you can see, right? So that's what I wanted to do. So let me now just share the PDF.
That handout, if we write handout, then no pauses, then directly will come, right?
With handout, no pauses. Without handout, pauses will come. So I just have to remove the handout. So let me take the PDF file. What did I do to the PDF now? Is it okay? Is it like usual days?
Yes, sir. Now it's
Oh, very good. So let's start now. So this is what we have been doing in the last few classes. We know the formula for L of f prime. So quickly let's recall, when f prime is inside the bracket, that is derivative with respect to t, what is the main thing on the output?
S into L.
S times LF and maybe an adjustment with y0, I mean f of 0, whatever. And when integral is with respect to t inside, what is the
Divided by S.
divided by s? And now I am taking derivative with respect to s, and the effect is multiplication by
minus LTF of
minus of LT or L of minus t. So it is basically multiplication by t, but inside with appropriate sign. And when you integrate outside, what is the effect? It is division by t inside, L of ft by t, right? And then we had the convolution operator. And what is the beauty of convolution? What is L of f star g?
L of G.
Yeah, convolution is a complicated operation, and Laplace transform converts convolution to usual multiplication. So all this will be very useful in solving IVPs. And using all these tools, we now have some idea how to find L inverse of a given function. By the way, what is the keyword which made L inverse a well-defined operation? One word in your
Lurch.
Lurch. Very good. Excellent. And so what was our slogan in the last week? I put something in highlight, no? Plain English. How do you do these things?
Experience.
Experience.
I said there's no theory. It comes from your practice. So what you have to do is spot the obvious and then modify. So, something should strike you in a given problem. Something should strike you, and then, you will start imagining various functions whose possible Laplace transform it is, and then you will have to tinker with it. You will have to modify it appropriately. And so it's practice. That's what I'm trying to stress. Okay. So today we will with an important class of step functions. Okay, till a point, some value, and then there is a jump discontinuity, and then another value. These are called step functions, and we will do Laplace transform of that. And that's what the new part today will be, but that's very easy. So let's do a few problems before getting into that. So let's do this. And this is my last slide. I went very fast, so I'm putting it once again. What is the key idea here? This is about partial fractions. This is nothing to do with our course. I'm just giving you a technique in order to write partial fractions. So if you have, x minus xi square, etc., using differentiation, you can get this coefficient easily. Can some of you, one of you recall what was the formula for this coefficient? What you have to do is multiply your function with the highest power coming here.
Some limit.
Yeah, multiply with the highest power coming here. So the given function fx, multiply with the highest power coming here. So x minus xi power ki. And then you have to take enough number of derivatives. And the correct number of derivatives is, if you are looking for the jth coefficient, you take d ki minus j. Ki is the highest power. Okay. Up to ki minus j, you take the derivative and take limit as x going to xi and divide by the appropriate factorial. This is obvious, this is just your calculus. This is from Taylor expansion. Please mute all of you. So this is just from the Taylor expansion, right? If you had this coefficient, if you had only, if ki was 1, it will be ai1 by x minus xi. If you multiply by x minus xi, what will you get? You will get ai1. And then no need to take a derivative. If you take the limit as x going to xi, it's a constant ai1, you have got the coefficient. If this term is there, then you will have to take derivative once. You can just take a simple example and see. So this formula you can use. Make sure that in Taylor expansion you will have this coefficients will have this factorial, so you'll have to do it appropriately. In the special case, when something is a simple root, ai is nothing but pxi by q prime xi. What is px and qx here? You are writing the function fx as px by qx. It's a rational function which you want to write as partial fractions. You write as px by qx, and if all the roots are simple, once again recall what is simple.
Multiplicity is 1.
Multiplicity is 1. In which case this formula simplifies to just take q prime xi. Otherwise you may have to take you may have to apply this formula. We will see some examples. You can work out more examples.
What are px and qx?
Fx you write as px by qx. Okay. But this formula you should apply only if you know everything is a simple root. Otherwise you should apply this only. Let's see some examples. And as we discussed last time, if you are getting complex roots, then you will have to combine together club conjugate terms in order to get partial fractions over R. Let's solve this IVP. What is the first?
Sir, was that f p upon q dash applicable for any ai, ai2, ai3?
Yes, we will see some examples. Then it will be clear. And then this is just basic calculus, not even basic calculus. It's much more simpler than that. Okay, as we do examples, it will be absolutely clear to you. What is the first step in order to solve the IVP? I'm just recalling from previous lectures. What is the first step?
We take the Laplace transform on both sides.
Apply Laplace transform. And then you make this assumption, right? Which we don't write down these days. What is assumption? After applying Laplace transform, so this you
Y
get.
double dash, y dash or exponential orders.
Yeah.
And
assume there is a solution which is piecewise continuous of exponential order. So you can apply your formulas. So you are applying the formula to L of y double prime will be this much, and L of y prime will be this much, minus 6 L of y equal to, how do I get 1 by s? It is L of 1, right? L of 1 is 1 by s. So I get this. And now you substitute y of 0 is 0 and y prime 0 is 1. Make the substitution. So you will get L of y. What will you get? You will get s square plus s minus 6 times L of y. Can you tell me what will you get? This goes, no? This goes, this is minus 1. So you will get 1 plus 1 by s, right? So you will get
then how
1.
y prime here again?
Y prime 0 is 1, right?
Yes, sir.
So that is minus 1. And this goes away, this goes away. So you will get 1 plus 1 by s. So you will get s square plus s minus 6 times Ly equal to 1 plus 1 by s, which is s plus 1 by s. So that you have divided. So you agree? This is what you get, right? Now you have to write this as partial fractions. So when you write it as partial fractions, yeah, so you see that this is nothing but s plus 3 into s minus 2. Can you quickly tell me partial fractions? What is the answer? You do it in your favorite way. And tell me the coefficients. I hope you are doing it. I am waiting for you.
Minus 1 upon 6s.
And the other coefficient for s plus 3?
Minus 2
Minus
by
1.
50.
Minus
1 by 5.
1 by 5. And the other one for 2?
Half plus half.
Okay, so I will see whether you are right or not in the next slide, but let me ask you, how did you do it? You did it in your usual way, or did you do differentiation?
Minus 2 by 15, sir. Sorry.
Minus 2 by 15. Okay, very good. How did you do it? In your usual way or this way?
Usual.
Usual way. So it's up to you. Okay, nobody is telling you should do it this way. You see, you take a few examples and you see whether your usual way is easier or this way is easier. Whichever is comfortable for you, you do it in that way. Okay. So is there an extra pause here? Yeah, there's an extra pause. And so let us do it. So PS is S plus 1. I'm illustrating that idea, P by Q. So PS is the numerator and Q is the denominator, which is S cube plus S square minus 6S, right? You have to multiply and write. So S cube plus S square minus 6S. Does Q have simple roots? Q has simple roots, no?
Yeah.
Yes, sir.
So I can directly apply Q prime S is this 3S square plus 2S minus 6. So I can directly apply P by Q prime. So P by Q prime at S equal to 0. At S equal to 0, what is Q prime? At S equal to 0, it is minus 6 and this is 1. So it is 1 by minus 6. So I got minus 1 by 6 as the coefficient. At S equal to, this corresponds to S equal to minus 3. So S equal to minus, right? Root is minus 3. So at minus 3, what is PS? Minus 2. And at minus 3, what is this? 27 minus 12. 27 minus 12 is 15. So minus 2 by 15. And at S equal to 2, what is the coefficient? 2, this is 3. And this is 12 plus 4 minus 6. So 12 minus 2, that is 10. So this is also quite easy. So I get all the coefficients. So I get this answer. So what is Y? What is Y? Y is? What is inverse Laplace of 1 by S?
1
1.
And what is
e power minus 3
and 1 by S minus 2?
e to the power 2t.
t.
The answer is minus 1 by X plus 3 by 10 e power 2t minus 2 by 15 e power minus 3t. Okay. Let's do one more example. So here, you know, the right hand side is for t. So, you know, we may give 4x, we may give 4t, we may give 4 alpha. It's clear, no? What is the meaning? Okay, we will give t or x only, not alpha, because alpha may be a constant. So if there is a t here, t is not a constant. That means y is y of t. Okay. If it is x here, that means y is y of x. So it is slightly different. And Laplace transform method will apply here also. So let us see what is the first step. Apply Laplace transform. So you will get s square ly minus sy0 minus y prime 0 corresponding to this minus 3 times sly minus y of 0. So this much plus 2 times l of y, and this is 4 times Laplace transform of t is Laplace transform of t power n is n factorial by s power n plus 1, right? So it is 1 factorial, so 1 by s square. So you get this. Agree? Now plug in this thing. Y of 0 is 1 and y prime 0 is minus 1. So when you plug in all that, let me not get into the detail, plug in all that and simplify. If there is no typo, this is what you get. L of y is this. You have to write this as partial fractions. Okay. So you have to, this is your P and this is your Q. Can I directly apply Q prime X here? No, because 0 is not a simple root. It is a double root. Okay. So I'll apply my formula. Okay. I will apply my formula. Need to write this in partial fractions. So coefficient of 1 by s minus 1. What will be our formula? Formula is you have to multiply with
1
recall the formula. Formula is
s minus 1
you have to multiply with x minus xi, the biggest power, times fx, and take the appropriate derivative, take the limit and do this. Okay, so s minus 1. So in terms of s minus 1, if you write here, right, we are here. So s minus 1, what is the highest power? 1 only. So you have to multiply by s minus 1. Okay, so you will get s cube minus 4s square plus 4 by s square times s minus 2. And
one is a simple root, so we can directly use p by q dash, right?
well, I want to be careful because I stated it. Yeah, maybe you are right, but I need to double check. I said if all the roots are simple, you can directly write. But maybe what you are saying is correct, but let me be careful. Okay, let me apply the formula. So this is What is this? This is s cube minus 4s square plus 4 by what do you see here?
Four
Yeah,
is
I think you are right. So this is directly q prime, right? So once again, here I said, yeah, that is true. I have written clearly here in the special case when xi is a simple root, you can directly apply. So that's what I have done there. So what will be my polynomial? Not this slide, right? So what is this? You have to multiply everything out. So you will get something. So what is this answer? This is s power 4 minus 3s cube plus 2s square, right? You have to take its derivative. So s power 4 minus 3s cube plus 2s square. So this is the derivative. Apply at 1. This, as one of you pointed out, this is because 1 is a simple root. So you're directly applying that, and this you get some answer. Coefficient of 1 by s minus 2 is similarly same thing. You apply a 2, you get some answer. Coefficient of 1 by s. What do you do?
apply that formula.
Apply that formula. So what do you have to multiply with? The highest power, right? So you have to multiply with s
X
square and take, do you have to take derivative or you don't have to?
There will
Derivative
be
is, yeah, derivative is highest power minus what you are going for. So it is 2 minus 1. So you have to take one's derivative. So it is limit d by ds of, you're multiplying by s square. So this remains. And you are taking d by ds, and then you take limit as s goes to 0 and 1 by 1 factorial. So that goes away. And you get some answer. And coefficient of 1 by s square, what do? You multiply by s square, so you get the same thing. Do you need to take the derivative? Do you need to take a derivative in the next step?
No, sir.
No, because derivative you are taking ki minus j. So here it is 2 minus 2, that is 0. So 0 derivative. So you don't have to take it. So you get 1 by 0 factorial, limit s going to 0, thus you get some answer. So this is a way of writing partial fractions. If you are more comfortable with your usual way, you go ahead, do that way. So you got some answer. So what is y? What is y? 1 by s corresponds to 1. 1 by s square corresponds to
T.
t, and 1 by s minus 1,
E
e
power.
to the
1 by s
T.
minus 2 e power 2t. So 3 plus 2t minus e power t minus e power 2t. So that's how you do it. Okay, now let me do a little bit of theory, and then I will do more examples from whatever we have covered till now, if time is there. If time is not there, I will postpone it to tomorrow's lecture. Okay, so tomorrow also please do attend the lecture. We will do many interesting problems. So for C positive, positive meaning non-negative, you are considering this function. So this is a step function, right? UCT. It is for t less than c, it is 0, and t greater than or equal to c, it is 1. So you can visualize 0 up to c. C is a positive function, a positive number. Up to c, it is 0, and beyond that, it is 1. So it's a step function. There's a name for this function, especially in electrical engineering and all, they use this name. Does anyone?
Heaviside theta function.
Yeah, heaviside function. Okay. Heaviside theta do they call? So here I should call heaviside u function because u is my notation. Let me call it heaviside function. Okay. So in 2016, I remember it was also part of my slides, but you know, I felt a bit shy because everything is being recorded. So I deleted the line here, which is that. And I did not think of it before. In the class itself, I just said that this function has a heavy side here and a light side here. Okay, so it's a joke from 2016. Okay, so heavy side function. And example, let us write this piecewise continuous function in terms of heaviside functions. Can you tell me the answer? This you should write as a linear combination of heaviside functions. How will you do it? Because now we are going to do Laplace transform of heaviside function, and once you have piecewise continuous things like this, you should be able to convert to heaviside and then do Laplace transform. So can you write this as a linear combination of UCTs? for various C? You can do and tell me the answer, and then I will check whether it matches with my answer. So this is the definition. UCT is up to C0, beyond C1, and we should write this as a combination of Heaviside functions. So you'll have to multiply, right? UCT will be only 0 or 1. So you may have to multiply with these coefficients appropriately. But how do you do it? If one of you have the get the answer, then tell me.
So I think it's 2u0 of t
Yeah.
plus u4 of t minus 6u7 of t plus 2u9 of t.
Okay, so tell me once again, 2u
0 of t
0 of t. Next
plus
step.
3u4 of t.
And are you getting 3 because of 5 minus 2?
Yeah.
Okay, and then?
And then minus 6u7 of t.
That is minus 1 minus 5, yes. And then 1 minus minus 1. Okay. So
Yeah.
you can just verify. You take an arbitrary point and verify what you got, and this function they match, right? That's how you double check. So let's take the point 5. At 5, the answer should be 5. And in your formula, at 5, the answer is 5.
Yes, sir.
Okay. So then it should be correct. So this is how you would have done it. If you have a function UC minus UD, then where is it 1? UC is 1 beyond C, and UD should be 0, right? In order to get 1. So UD should be 0, so it should be less than D. So if it is between C and D, it takes 1. You agree? That's the definition. And 0, where will it be 0? It will be 0 below C, and it will be 0. It will be 0 above D also, no? Above D, it will be 1 minus 1. So everywhere else, it will be below C, it will be 0, and above D also it will be 0. So this is the first observation, and from this you can do what this person just pointed out. I'm sorry, I'm not seeing the name, so I'm saying one of you, this student, etc. Because I can't see the names when you speak. So f of t equal to 2 times u0 minus u4 plus 5 times u4 minus u7 minus u7 minus u9 plus u9, just from this observation. UC minus UD is 1 here and 0 everywhere else, and then you write it down as a linear combination. So you get 2, 3, minus 6 and 2. Okay, so that's how you do it. And the question is, does Heaviside has a Laplace? Okay, so answer is yes. So let us just do it. L of UCT at S will be, by definition, integral 0 to infinity, e power minus st UCT dt. And what is an obvious next step? What is the next step? You tell me.
We divide them, integral 0 to C and C to infinity.
Yeah, so UCT, you just apply the definition. So you will get 0 to infinity, C to infinity, e power minus st dt. You agree? Because otherwise it is 0. So integrand vanishes. And this is e power minus st by minus s from C to infinity. And that is minus of minus. So that is plus. It is e power minus cs by s. What is your assumption in doing this integration? SS?
Positive. S is positive.
Positive, because only then you plugged it in correctly. So you are getting this answer which is valid for S positive. So this is the answer, Heaviside of Laplace. No, Laplace of Heaviside. Okay. Now suppose f is a function from R to R, and you consider the new function gt to be, when t is less than c, you take 0, and f of t minus c if t is bigger than or equal to c. So this is a function of the form that we have considered, and obviously gt is uct times f of t minus c. Okay. And now we can do, suppose L of t is f of s. Suppose L had a Laplace transform, f had a Laplace transform, capital F of s for s bigger than a, and if c is positive, then you have a formula for this new function. So you are doing t minus c and multiplying by a Heaviside function, and then that is nothing but e power minus cs fs. This matches with this observation, right? This matches with this observation. What was the function small f in this calculation? UCT times f of t minus c. F is constant function 1. When f is constant function 1, left hand side is this and right hand side is e power minus cs times Laplace transform of 1, which is 1 by s. And we are saying the same thing is true for any function. And do you think the proof is easy, or we need to do some work? Do you think it's obvious? It's exactly that calculation. You just integrate.
Sir, can you please explain the theorem again? The statement of the
That's what
theorem.
you see here. You have a function f and its Laplace transform is given to you. Okay. So this function, if you translate by c and multiply by the corresponding Heaviside function, then its Laplace transform is the original Laplace transform multiplied with the factor e power minus cs, where c is this c. Is that clear?
Yes, sir.
Okay, so proof is obvious. You just apply the definition. What is the definition of Laplace transform? Integral 0 to infinity e power minus st times this function times dt. Agree? And now this will be integral from where to where? Integral from
C to infinity.
c to infinity, because otherwise it goes away, and c to infinity UCT is 1. So it is this. And what is your last step? One obvious step is
Substitution.
E minus C equal to K.
yeah, t minus c, put something equal to t minus c and make the change. So I call t minus c to be u, dt is du, and t is u plus c. And when u is t minus c, when t equal to c, u equal to 0. When t equal to infinity, u equal to infinity. So you got this. And out of this, e power minus cs comes out. It has nothing to do with the integrating thing. So e power minus cs comes out. And what remains is e power minus su fu du integral 0 to infinity. That's exactly the Laplace transform. Okay, so you have proved this. So this also will be useful. Example, find the Laplace transform of this function. It is sine t when t is between up to pi by 4 and t is bigger than pi by 4. It is sine t plus cos of t minus pi by 4. You can apply this formula, or you can do it directly also. So you don't want case by case thing. That is the point. You don't want case by case. You want to write it as one function, and you can use this step function, Heaviside function, in order to do that. So the given function is sine t plus u at pi by 4 of t cos t minus pi by 4. You agree? When t is less than pi by 4, this is 0. So this goes away. So answer is sine t. And t is bigger than pi by 4. This is 1. And you get this answer. Now you can apply Laplace transform. It is L of sine t plus L of this thing. And L of sine t is what? L of sine t is
1 by 1 plus s.
1 by s square plus 1. And this one, your formula is e power minus cs. So e power minus pi by 4s times the Laplace transform of the function cos t, right? In your theorem, it is Laplace transform of the function f of t. So if you have f of t minus c here, it is e power minus cs times the Laplace transform of function f of t. So here you have Laplace. So what you have to write here is e power minus pi by 4 s times the Laplace transform of which function? Laplace transform of f of t. F is cosine. So Laplace transform of cos t, which is s by s square plus 1. So that's the answer. Okay, so very, very useful. Though it is very easy, very useful in order to do this kind of step-by-step in this kind of case-by-case functions. The function is defined case by case, and if there is a jump discontinuity, you write it as one line using the Heaviside function and apply this formula. I hope it's clear. Let us do the inverse, right? Whenever you had a function, whenever you had a theorem, you had a Converse theorem. When you had L of f prime, you had L of integral of f. When you had L of f prime, you had integral of L of f. Similarly, there's a Converse theorem to that. Suppose L of ft is fs and let c be some constant. And then earlier, what did you do? Earlier, you did L of a translate of f. And the answer had multiplication by e power cs with a minus sign. Now you are doing translation outside. In the Laplace transform, you have a translation, and that corresponds to multiplication by e power ct inside. Right? This is exactly parallel to this, no? It's a converse of this. Here you had translation inside. You remember we had derivative inside, integral inside, derivative outside, integral outside. And this is translation inside. Then you had multiplication by exponential outside. And now I have translation outside, meaning in capital F, I have translation that corresponds to multiplication by exponential inside. Okay, so if you have translation outside by C, that corresponds to multiplication by the correct exponential inside, and there is a correct range which will come from the proof when S is bigger than A plus C. Okay, so this proof is also very easy. You do this thing, this side, L of e power ct ft is, just plug in the definition, integral 0 to infinity, e power minus st, e power ct ft dt. What is the next step? Combine these terms, and what is the next step?
Substitution.
Do you need to substitute? There's no need to substitute, no. Why do
Oh
you
yeah, it's directly we can.
This is exactly the answer. This is exactly the answer. Okay, so all this makes sense in this range. So it is even easier than earlier. There's no substitution also. Okay, so this is obvious, and this also you should keep in mind. This will be very easy. Okay. Now let us find the inverse transform of this. What do you do first? What is the point of doing this? So write this as what there is a term.
Complete the square.
What is the term?
Completing the square.
Completing the square. Yeah. For one moment I blanked out. I didn't get that expression. Completing the square. Yes. So you complete the square. What is the answer?
S minus 2 whole square plus 1.
Yeah, s minus 2 whole square, and that minus 2 is suggestive because you see minus 4 there. So s minus 2 whole square will have plus 4 and plus 1. So this is s minus 2 whole square plus 1. And that is useful because s minus 2 whole square plus 1 reminds you of what? After the translation, it is like s square plus 1, right?
Yes, sir.
And s square plus 1 reminds you of
Cos t.
cos of sine.
Sine.
Yeah, it is sine because
Yes, sir.
numerator is constant, so it reminds you of sine, and the translation we can take care of by this thing, right?
Yes,
1
sir.
by s minus 2 whole square plus 1, what will be the answer? 1 by s minus 2 whole square plus 1 is f of s minus c, where f is the function 1 by s square plus 1, no? So what will be the inverse Laplace transform of 1 by s minus 2 whole square plus 1?
E power 2t sine t.
E power 2t sine t. Very, very good. So complete the square, and this is f of s minus 2, and the fs is L of sine t, and therefore L inverse of this is e power 2t sine t. Easy, right? So each one of these steps is easy. Okay, nobody will say this was difficult or the previous one was difficult or the previous one was difficult. But what can become difficult under time pressure in an exam? Right? We have many theorems. We have many. Yeah, tell me.
Thinking.
Thinking, yes. Thinking, yes. But what I had in mind.
Silly errors.
Yeah, say that again.
Silly errors.
No, that of course, that is true for any exam. But I'm talking in terms of Laplace transforms. What can become a bit difficult, especially under time pressure, is that, see, this particular trick is easy. The previous particular trick is easy. The trick before that is easy. All this trick individually is easy.
Knowing what the trick is.
All these things together, right? In one problem, you may have to apply multiple tricks. And you may be able to do it in several different ways. So if you are really, really comfortable, then you will do it in the easiest possible way. So it can get a bit more complicated than in my lecture slides because I might club. Okay, we might club these tricks together. We may not also, I don't know. Okay, so exams, as is the case with my lectures, questions are also decided only at the very end. Okay, so depending on, our, so both of us will decide it together, and depending on our energy levels and our sharpness at that time, etc., questions may become easy, difficult. Questions may have a typo. Fortunately, our quiz did not have a single typo, but it is rare, right? Usually you would have seen that in exams there are typos, in which case, we may have to withdraw the question, etc. So these things are possible. So we will see. But I'm challenging you to work out enough problems using all possible tricks. Also, frame questions and ask your friends. Let them solve your questions and you solve their questions. Okay. Be very, very comfortable with it. And as I usually say, not just for, our exam or our course. These are important things anyway in engineering. Okay. So you should be much more comfortable with these things than me, for example. Okay. So let's do one more example. Solve this. All the terms are clear, no? There's nothing difficult here, right? The only new thing is this kind of function, but this kind of function also U5t and U20t we have introduced. By the way, I'm not 100% sure what the other instructor's notation is for the Heaviside function. Okay, so in case in the exam you see another notation, if this is the notation for both of us in D1-D2 and D3-D4, then we will not say in the question paper. See, we also want to make the questions as small as possible, as short as possible. So if this is our common notation, we will not explain that this is a Heaviside function. Okay. On the other hand, if the notations differ, then we might employ one of the notations, and in which case we will say what we are talking about is a Heaviside function. So most likely the notations are same because our basic source file is the same, and we may make some changes here and there. So if it's the same, we will not explain it. Otherwise, we will explain it. So whenever, we have common notations, not just here in any topic, we may not explain it in the question in the exam. It is understood. It is a common notation from our slides. And similarly for our common conventions. Okay, so with all this, so what is the first step? Apply Laplace transform. So when you apply Laplace transform 2 times, we are assuming there is a solution piecewise continuous of exponential order. So L of y double prime is this. L of y prime is this, and twice L of y equal to L of the right hand side. Now we know all the terms, so you can plug in y of 0 is 0, y prime 0 is 0. When you do all that, you get 2s square plus s plus 2 times L of y equal to, all the other things goes away because y of 0 is 0, y prime 0 is 0. And is this okay? What is L of u5? It is e power minus 5s by s, and u20 is e power minus 20s by s. So this is clear. So now what we are doing is, this side anyway you have a result to understand, right? If the Laplace transform has a multiplication, you know how to guess the inverse. If the Laplace transform has a multiplication by e power minus cs, you know how to guess the inverse Laplace transform. You have to translate and multiply by a Heaviside function. So that part is okay. That part is not difficult. So what you have to do is, you have to find out this only, right? Inverse Laplace transform of this is what you have to find out. How did I get this? There is a 1 by s here, and there is 2s square plus s plus 2. These translations are okay. We will deal with it at the end. So this you have to write as, so if L of h of t is h of s, if small h is the inverse Laplace transform of this, then what is the answer? What is y in terms of h?
U5 minus U20 of
E power, once again, let me see the theorem. This is the theorem, right? E power minus 5s times the Laplace transform. So it will be u5 times
h of t minus 5.
minus 5, that will give you that, and then correspondingly for 20. So your answer will be, where are we? Here. Your answer will be u5 h of t minus 5 minus u20 h of t minus 20. Okay, so h of t you do in the usual way. So here I am not using my method, here I am using your method. This is how you do it, right? A by s plus bs plus c by 2s square plus s plus 2, and you solve. Suppose we wanted to do this method, how will you do it? You have to find the roots of this, and you may get complex roots, I don't know. So what are the roots of this 2s square plus s plus 2?
Definitely complex.
Definitely complex, because b square minus 4ac is, yeah, it's negative. So you will get complex roots, so that's good. You will get simple roots, so you can do px by q prime x, and the complex things you combine together. So like that also you can solve this. So solve that way also. You got some answer, and therefore you got some answer. And here what I am doing is half by s is okay, and here what you are doing is completing the square. So this step is important. What you are doing is 1 by 2 you have taken out. So what you have is s square plus s by 2 plus 1 by 2. So s square plus s by 2, when you complete the square, you got 1 by 16. And what you want is 1, no? S square plus s by 2 plus 1. And in order to get 1 by 16 plus 15 by 16. And because there is an s upstairs also, I have to write that also in terms of s plus 1 by 4. Only then you can get that s plus something by s square plus something thing. Okay, so this, what will you do in your next step? So forget till here. Let us just focus on this. Tell me what is the next step in order to find inverse Laplace transform?
Let f equal to 1 s plus 1 by 4 divided by s square plus 15 by 16.
Will you do it together, or will you do it in two ways? Will you divide it into two parts?
We'll split it into two.
Yeah, you have to split it into two parts, because there is a cosine and there is a sine both coming here, right? So for 1 by 4 divided by s plus 1 by 4 whole square plus 15 by 16, what is your inverse Laplace transform? 1 by 4 divided by that thing. What is your inverse Laplace transform?
4 by 15 into sine of, I think, sine of s plus 1 by 4 divided by 15 by 4.
Correct. Root 15 by 4, no?
Yes, sir.
Yeah, correct. So 1 by 4 is a constant that you take out. So you have to worry about 1 by s plus 1 by 4 square plus 15 by 16. So that is of the form 1 by s square plus root 15 by 4 whole square. So 1 by s square plus a square. So that is 1 by a sine t. So you will get, no, sine 80, right? 1 by a sine 80. So that 1 by a is also a constant. So you're getting sine 80. So you're getting sine root 15 by 4t. Agree? That's what you're getting, that part, but you have to make the shift, no? Because it is not s, but s plus 1 by 4. And which theorem are you applying here? Are you applying this?
Yes, sir.
Yes.
So you have to multiply by e power. What is your c here?
Minus 1 by 4.
4 minus 4 minus 1 by 4.
Minus 1 by 4. And then you do this part, s plus 1 by 4 by this thing. So that is of the form s by s square plus a square. So the answer is cos 80. And there also you apply the shift. So the answer is 1 by 2 by s minus 1 by 2. Yeah, this is what I have written. S plus 1 by 4 by this. And here I have written this in the form a by s square plus a square. Only then you can apply. So one more adjustment is required. 4 by root 15 you multiply and divide, and now this is of the form sine 80. So ht is half, because 1 by s inverse is 1, minus half times, this reminds you of cos 80, where a is root 15 by 4. So you got cos root 15 by 4t, but it is not s, but s plus 1 by 4, that resulted in multiplying by e power minus 1 by 4t. And similarly, minus 8 minus 1 by 2 root 15 is just this multiplication. This is sine root 15 by 4t, and you have to multiply by e power minus t by 4. Okay. So in all these steps, you can make a silly mistake. What you call a silly mistake can be made under time pressure on all these steps, because you know here you have to write the correct one in the numerator. Only after that you could do. So as you can imagine, it's very easy to ask questions where you can make mistakes. So naturally, an exam where these kind of things are there, you cannot say it will be so easy, right? Because even if the question is easy, and even if conceptually the answer is easy, in an objective type exam, you can easily make, a silly mistake. So be very, very careful, practice a lot. That's all that I can say. Okay, let's do one more example. My title has changed. Did you notice? Up to now, the title is title of the slide. What is the title of the slide in all these previous things? My title was throughout
Laplace transform.
Laplace transforms. And did you notice the next slide? What was the title? It was too quick, maybe you didn't notice. Did anyone notice the title of the next slide?
Winding up.
Winding up. So course is coming to an end. Actual winding up will be tomorrow, but today itself I am. So if we are in a flight, what are we doing? We are preparing to land. Okay, so we are slowly. What is the correct word? What do they announce? We are starting our descent. Is that the correct word? Correct terminology? Of course, we have all forgotten about flights. We haven't traveled in a long time.
They will say landing only. No?
Landing.
We are going to land.
Some of them announced, no, we are preparing for our descent or something like that. Yeah, preparing for landing, let us say. So we are also starting our landing. So I hope, maybe this is the time for the captain to thank the passengers also. So I hope you had a comfortable journey. And they also say that, what do they say at the very end? We hope we can serve you in the future also, etc. So I don't know whether I'll teach another BTech course. Anyway, you don't have so many maths courses. So anyway, once you are back on campus, if you feel like no compulsion, come to my office and say hi. Okay, so let's start winding up. Let's do some examples. So L of e power t minus t sine square t. Why don't you make some comments and then we will go through the slides. What are the ideas here?
First e power minus t is there, so we can transform that one.
You can transform, and therefore you have to worry about sine square t. And what is the idea to do sine square t?
You can write as minus cos 2t.
Yeah.
Cos 2t.
Sine square t directly, there's no technique that we have done, right? So sine square t you write in terms of cos 2t. So this is L of half of e power minus t into 1 minus cos 2t. Now everything is okay. Again, what is the theorem that we are applying? If multiplication by exponential is there inside, you can do this and translate s minus c. So what is the answer corresponding to 1? Answer corresponding to 1 is, what is L of 1? Half anyway you take out, and L of 1 is
1 by s.
1 by s, and therefore what is the translation?
1 by s plus 1.
1 by s plus 1 or 1 by s minus 1? E power minus cs minus ct or e power ct? So be careful about all these things. E power ct is f of s minus c. E power ct is f of s minus c. Whatever you are multiplying, the coefficient in the exponential is subtracted. So here it will be
Plus 1.
Whatever is there is subtracted. So minus 1 is subtracted. So s minus minus 1. So s plus 1. And here L of cos 2t is
S by s square plus 4.
S square plus 4. And again you do the
S plus 1.
Yes, you change s to s plus 1. So clear? Half times 1 by s plus 1 minus s plus 1 by s plus 1 whole square plus 4. Next example, L of t square e power minus at. How do you do this?
S to s plus a.
So you can do in various ways. Okay, what is the way that if you want to do it like this, what do you see? You have to do L of t square, right?
Yes.
So what is L of t square?
Applying convolution method.
Well, you have known by convolution. Can't you apply this theorem? Same technique can't you do? You can do this technique, no? You're multiplying by e power minus at to t square. So if you know L of t square, you can apply the corresponding shift, right?
Yes, sir.
What is L of t square?
2 factorial
cube.
over s cube.
So 2 by
S cube.
S cube.
and there is a minus a, so you change s to s minus minus a. That will be the answer, no? So that will be the answer. Tell me what is that answer is. So I'm doing it in a different way here. What will be the answer if you do like that? 2 by s cube. So what is the answer? 2 by
S plus A.
S plus A cube.
by s plus a whole cube. Just write it down. Let us see whether our answer matches with that. 2 by s plus a whole cube. And what I'm doing here is multiplication by t inside, right? Minus t inside corresponds to taking derivative, right?
Minus times derivative.
Yeah, derivative of the Laplace transform of this. So e power minus at is 1 by s plus a. Multiplication by minus t corresponds to taking d by ds. Multiplication by 1 more minus t corresponds to taking 1 more d by ds. So it is d square by ds square of 1 by s plus a. What is this answer if you do?
2 by s plus a whole cube.
Minus 1 by s plus a square and again minus 2. So 2 by s plus a whole cube, no? Correct?
Yes, sir.
Yes.
And this is the answer that we got in the other method also, right?
Yes, sir.
What is the other method? Other method is do L of t square and apply the shift. Apply the shift will be s going to s minus minus a. L of t square is 2 by s cube and change s to s minus minus a, which is s plus a. So you can do in various ways. We have so many techniques. Next example, L of t power a e power minus bt. So yeah, this is the point. Will you do d by ds 8 times or will you do this method? The other method that I said. What is your favorite method now?
Other method.
Other method. Two reasons. One, if a is 1000, you have to differentiate 1000 times, which you don't want to do. Another reason is who said a is a natural number? A may not be a natural number here, right?
Yes, sir.
Therefore, only this method, the other method works. Differentiation method will not work. If a is 1.5, there is nothing called taking derivative 1.5 times. No, okay. I know that some of you will talk about fractional derivative, but I don't know what that is. Okay. So, and I have no idea what fractional derivative is. For me, there is no fractional derivative. So if a is 1.5, I don't know how to differentiate. And therefore, only this method is there. So what is the answer? I'm not telling a is a natural number in general. What is the answer?
Gamma a plus 1 by s plus b whole power a plus 1.
Very good. Gamma a plus 1 by s plus b power
A plus 1.
Plus 1.
plus 1 or a?
A plus 1.
A plus 1.
What is gamma of t square? Yeah, cube k. Yes, correct. So gamma of a plus 1 by s power a plus 1, but s is going to s minus minus b. Do you agree that this is a very beautiful part of mathematics, Laplace transform? You are getting very, very good techniques, right? And so easily by applying all your results, you are able to write down Laplace transforms. And all this will be useful in solving IVPs. Okay. Oh, is it time? Can I take 5-10 more minutes because I have a very beautiful example coming up.
Okay.
Is Monday a day when you have an immediate another class?
No, sir. Monday we don't have idea. For us,
I
it
can
is.
continue for 5-10 minutes, no?
Yes, sir.
Is that okay? Because it's a very beautiful example. You are going to get thrilled with the next example. Next or next to next, I don't remember. But I did see in my slides, there's a very beautiful example coming up. So let's continue. Anyway, tomorrow is our next lecture. Let us finish whatever is there today itself, so that tomorrow there's not much. In the very last lecture, I don't want to exceed time. Also, Tuesday, you have a class soon after, right?
Yes, sir.
Tomorrow you have a class soon after, so I will not be able to extend. So let me take some more time. Please don't quit. Please be in the class because next example is my most beautiful example. Okay. Next or next to next, we will see. Not this, maybe after this. Okay. So what is L inverse of this? Can you tell me?
We need to factorize that down one, right?
Yeah. So maybe that is one way you can factorize, but then complex numbers will come, no? That's okay. Let complex numbers come. You can do that way. So definitely you can try that way. Okay. But what I have done here is I have used partial fractions in a particular way so that I did not have to deal with complex numbers. What you meant is s power 4 plus something as s square plus something times s square minus something, right? Is that what you meant?
Yes, sir.
Yeah, you can do that way. In fact, maybe, you know, most likely I would have done that way only in order to reach here. So you do that way, then write as partial fractions, but you will have complex numbers. You don't want final answer to have complex numbers, so you take conjugates in together, etc. Okay. So whatever way you have to come to this step. And once you come to this step, then the answer is clear. 1 by 8a cube anyway constant, forget it. How will you do this part? Let us just focus on this.
Take s plus a plus a, sir, numerator.
S plus a plus a. And here you write s minus a minus a. Then it's done, no? S plus a, you will have to write it as two things, right? S plus a by s plus a whole square plus a square will give you what? Cos at, but I have to change t now. So what is the answer? Cos a times
E minus.
t minus a. And s plus a. And that plus a by that will give you a sign, and similarly here. So I haven't even done it because by this time you know how to do it. Only this step was important. So I have skipped the rest of the thing. So you will get cos term here, sine term here, cos term here, sine term here. Okay. Next example is, you know, what is called a system of equations. You have more examples in your tutorial on Wednesday. This is a system of linear equation. What is a variable? Can you tell me?
Both x and y.
T.
T is your variable. So x is x of t and y is y of t here. And x prime meaning dx by dt, y prime meaning dy by dt. So you have given two equations simultaneously. Simultaneously you have to solve. We did not do any such thing in this course. But now that you know Laplace transform, you can apply, no? I didn't have to teach you solving system of linear equations, right? Apply Laplace transform and see what you get. Take Laplace. So you will get Sx. So capital X is a Laplace transform of small x and capital Y is a Laplace transform of small y. So you will get Sx minus x of 0, which is not given to you. So leave it as it is, equal to capital X plus capital Y. And similarly, you will get Sy minus y of 0 is 4 capital X plus capital Y. And you can solve for this. You will get x of s equal to something and y of s equal to something. This is already x of s, right? So you will get something, and you can solve for both together, right? Suppose x of 0 is given, y of 0 is given, you can solve. So system of equations also you can do. Though we did not cover system of equations till now in our course, Laplace transform technique is so powerful that system of equations also you can do. And I don't think I'm doing, you know, all these things because this will be techniques that, you know, do partial fractions and do it. So you can solve for both x and y together. So take x inverse, L inverse to get xt and yt. Okay. I think this is the, yeah. So here is one more. Is this a system of equations?
Yes, sir.
Three variables.
This is a system of equations, and you have y1, y2, and y3. These are all functions of
T.
t. Functions of t. So apply Laplace transform. In the first, you got 2s y1 minus s y2 minus y3. What is this notation? Capital Y1. It is the Laplace transform of small y1.
Yes, sir.
Okay, so similar. So you get the first equation. Second equation will be sy1 plus sy2, because you know y2 0 is 0, etc., equal to 4 by s square plus 2 by s. And similarly, third, you will get sy2 plus y3 as 2 by s cube plus 2 by s. And solve this. Solving, you get y1, y2, and y3. And therefore, you have got the answers as y1t is t square, y2t is t square plus 2t, y3t is t square minus 2t. Very, very powerful method. System of equations you are able to solve. Now you can, go back and check. T square plus 2t and t square minus 2t satisfies all these conditions and satisfies all these equations simultaneously. Such a powerful method. We never had system of equations in this course till today, the very last, last to last class, penultimate class. But there's nothing here, no difficulty at all. It is just system of solving 106 linear equations and then the theory of Laplace transforms. Okay, here is a simple theoretical looking thing, but nothing. So what do you call such a function?
Periodic.
What is the period here?
P.
Just seeing what will be the Laplace transform of a periodic function. So L of f is 0 to infinity e power minus st ft dt. Tell me what is the next step?
We'll divide break.
P to P to 2P like that we'll divide.
0 to p to 2p like that you divide. And what is the next step?
T equal to
Weight
x
all
plus
of them.
T equal to x plus 2P like that we'll divide in the
Replace. So this is as it is. Here you replace t with, here you replace t with t minus p. T with t minus p. So the p to 2p has become 0 to p. But this would be f of t minus p, no? Why don't I write like that?
You can convert it back.
Periodicity.
Because of the period. Because of the period. And doing it twice, you would have got t minus 2p here, etc. And this is exactly this, right? E power minus st ft dt from 0 to p is common. And what is coming out here is e power sp and e power 2sp, etc. You will get a geometric series, which is 1 by 1 minus e power minus sp. And what is
Sir, I think inside the bracket it should be t plus p, t plus 2p.
Okay, t plus p, in which case you have changed it to f of t. Yeah. Final statement is anyway true.
on the power, sir. On the power, e power minus s of, I think it should be t plus p.
Here.
Yes, sir.
Well, you can take t plus p or you can take t minus p, no? If you can take t plus p, then you can also take t minus p, no? Because of the period, right?
I mean,
Sir, the exponential is not periodic.
but expansion will be different, no? Here p to 2p we turned into 0 to p, no? Then it should be x plus p, no?
Okay, so what you are saying is here it should be t plus p?
Yes, sir.
So what
Then
is
only the formula will be,
so
then only this.
so tell me what is the change of variable here? U equal to?
Sir, but the final result is correct.
Yeah,
Final result is correct, but intermediate step is wrong.
Correct, but I am not convinced. So let me double check. What is, just take this second step. And what is your change of variable? U equal to?
T equal to
Minus
x plus
p.
p, sir.
T minus
T
p.
equal to x plus p, I am saying. Suppose.
So
Sir, t will be equal to u plus p.
I want to substitute u
equal to t minus
u equal to
t minus p.
u equal to t minus p. Then this is okay. And
Oh, sir, this is not
No, sir.
okay.
Sir, we are u
Substitute
equal to
t
t
equal
minus
to
p,
u
but
plus p.
but let me continue.
u plus
this.
p.
Let me substitute u equal to t minus p. Nobody can stop me, no? So let me substitute
U equal to t minus p. Okay, sir.
We change it t to u.
You are changing t to u, sir, not u to t, no? T
Variable of integration is changing.
Okay, so I'm changing. Okay, in my way of saying, I will say I am changing t to t minus p. Is that what you are thinking also?
T
I'm going
to
to
t minus p, yes.
minus p.
And then the integral limit will change 3p to 2p to 3p.
No, when I change t to t minus p, p will become 0 and 2p will become p.
No, sir.
No, sir.
Sir,
2p
t plus
to
p will come,
3p.
Instead of t minus p, t plus p is there.
Sir, you should consider taking T1, T2 so that we can identify what are you talking about.
Once again, I am saying I'm going to put u equal to t minus p. That is an allowed substitution, right?
Yes, sir.
What is du?
dt.
Then t u plus p.
No. No,
substitute t equal to u plus p.
forget t equal to 2 plus p. I am putting u equal to t minus p. That's all, nothing more. And
Both
my
are same.
in terms of u,
Sir, if you put u is equal to t minus p, then t would be u plus p. Hence, in the
okay, fine.
exponential, it would be u plus p.
Yeah, substituting u in place of t, then e power minus s of u plus p it will become, I'm saying.
Okay. So maybe you are right. Maybe you are right. So in which case, what are you saying here? What will be the change?
Sir,
In power, everything will be plus e power
Okay,
minus
that's
s
what
of
you
t
say.
plus
Okay,
p.
so I will double check. I will double check because we are exceeding time. And if there is a change, I am not convinced, but maybe you are right. If there is a change, I will change it here. And in which case, e power, okay, in which case only this answer will come, right?
Yes, sir. If I change to plus, then
So
come
if,
this one.
if this step is correct, then here there is a typo. If this step is correct, then here there is a typo. Okay,
Yes, sir.
we will check. Maybe you are right, and this may be correct. And here it may be plus. So e power minus sp, e power minus s times 2p will come, and under some condition on this being, but this anyway is less than 1 if p is positive. And in which case geometric series will give you this, so you get this answer. Okay, so here is one more thing. And what is the answer for this? How will you do this? How will you do this problem?
Beside.
Heavy side function.
Heavy side. And so I have not even done it, you see, because I just wanted you to say heavy side. That's only the key point. And this one? This one anyway, it doesn't matter. No, 1 point doesn't matter for integration, right?
Yes, sir.
You can just apply the definition, right? So dividing by t reminds you of what?
Integration.
Integration, right? Dividing by t inside L of ft by t. So you can get it out of Laplace transform of sine t, right?
And integrate.
Yes. So integration. So L of sine t by t is integral of L of sine t dt s to infinity. This was your formula, right? So what is L of sine t dt? L of sine t is
1 by
no, there is a mistake here, no? No, there is no mistake. Actually, there is a mistake because I should write this as L of sine t of x dx. But you know what I mean. So what is the answer?
1 by s square plus 1.
1 dx. And what is dx by x square plus 1 integral?
Tan inverse.
Tan inverse.
So when you substitute s and infinity, what is the answer?
Pi by 2 minus tan inverse s.
Pi by 2 minus tan inverse s. Okay. So this is what you got, L of sine t by t. And this is tan inverse 1 by s, no?
Yeah.
Okay, so you got tan inverse 1 by s. And from this, I leave it as an exercise. This is an integration you would have done in various different ways in your calculus class. Integral 0 to infinity sine t by t dt is pi by 2. And from this also you can compute that. Do you see how to do this?
Put s equal to 0 in first.
Because Laplace transform you have computed and you apply the definition of Laplace transform. It is integral 0 to infinity e power minus st sine t by t dt. In that, if s equal to 0, then the answer is tan inverse of infinity, and that is pi by 2. So here is a beautiful way of doing this in terms of Laplace transform. Okay, so exercise, that was an exercise. And how do you do this? This is easy, no?
Separate out
1 by t minus
1 by t gives you
1 by t gives constant function.
1.
Sir.
no, that is for 1 by
That
s.
is inverse Laplace. We have to do Laplace.
Integral s to infinity L 1.
T gives you integral s to infinity something, and e power minus t by t also you can do for t and adjust with e power minus t later, right?
Yes.
Yes, sir.
S plus s to s plus 1 you can change. So answer you can double check whether you get this answer, log of 1 plus 1 by s.
Sir, can you repeat?
What I'm saying is 1 by t you can do using integration, no? ft by t. F is constant function 1. I'm taking 1 by t. So that is L of ft by t, right? Where f is constant function 1.
Yes, sir.
Therefore, you can do that integration technique and do that part. And e power minus t by t also you have to do 1 by t only. No, you can change s to s plus 1 in order to accommodate e power minus t multiplication.
Okay, sir.
That's one way. There may be many ways. But the point is, you should remember that if you have this, then the inverse Laplace transform is this. Which also you can do, right? We have done a similar thing, no? Suppose, the question is, this is given and inverse Laplace transform you have to find. How will you try? What do you
First differentiate.
Yeah, what is noticed is there is an s plus 1. So by differentiating, you can get 1 by s plus 1 from which exponential will come and differentiation corresponds to integration, whatever. So that's how you will do it. So double check. This is what you are getting. Okay. I think this is my last example. And this is my beautiful example. My meaning, I must have copied it from somewhere, but in this course. Is this a easy differential equation or is it a not so easy differential equation?
Difficult.
It's not so easy because
taking Laplace simple.
It's not so simple because there's a variable coming here. On the other hand, it is not Cauchy-Euler either, because Cauchy-Euler would have had a t square here. That's not happening. So this is not so easy, but it's an IVP. Let us just blindly apply a Laplace transform and see what we are getting. Okay. So
we get differential equation in S.
Say that again.
We get differential equation in S.
Yeah, let us see.
First order.
Let us see. So let us apply Laplace. So first term gave you s square Ly minus s of y of 0, that is plus s, minus y prime 0, that is 0. Agree? What is the next term? T y prime, when you apply Laplace transform, what will you get?
Multiply by t, then differentiate by s of Laplace of f prime.
Yes. So you have to do L of y prime. You have to do L of t f t, where f t is y prime. So you have to do L of y prime and then you have to do d by ds.
D by ds L of y prime.
Exactly, with the correct sign, minus sign. Okay, so when you do that, you get, so I have written as L of t prime, ty prime itself, minus 2 L of y equal to L of 4. In the next step, you get 4 by s, which is L of 4 equal to s square Ly plus s. I have left it like that. And the next step will be what? It will be L of y prime and you have to do minus derivative. Minus 2Ly. All of you agree? This thing is completely understood. Okay, it is L of y prime minus L of t would have been another prime. There is a minus sign coming therefore. Okay. So this is s square Ly plus s minus of what is Ly prime prime. It is d by ds of Ly prime. So what I have done is I have just put L of y prime here. L of y prime is SLY minus y of 0. Minus y of 0 is minus of minus 1. That prime is remaining. Prime is remaining. In the next step, it is Ly prime, S of Ly prime plus Ly, right? Plus, this is, you are using product rule. S of Ly prime plus L of y with a minus sign. So minus L of y. Derivative of 1 is 0, right? So minus 2L of 1. You got this. So you can write this as s square plus 3 s square minus 3y minus sy prime plus s. So what have you got? What have you got?
First order differential equation.
First order differential equation. Because the multiplication by t came here, you are not getting a linear equation, but you are getting a first order differential equation in y, which you should solve. So you have got a differential equation y prime plus 3 by s minus s times y equal to 1 minus 4 by s square. This you have to solve. And you have various methods of solving first order equation, integrating factor and all that thing. When you solve, you're going to get this answer. Because integration will give you a constant. And this constant you cannot evaluate because nothing more is given to you. Okay. So how are you going to solve the problem? I am expecting a wonderful line, a thrilling observation from you. At least one of
Sir,
you.
sir, C
P
must be
equal to
0
0.
as the
Let's
Laplace inverse of
why?
some s tending to infinity should be 0.
Absolutely. Excellent. Here is a thing of beauty. C is 0. You know, just from the power of Laplace transform theory, we have concluded, you know, I will not bother about this constant. C is 0. And why is answered? Because this is a Laplace transform of a function. And therefore, limit as s going to infinity has to be 0. This is fine. This is fine. But this limit is infinity as s going to 0. So the only way is that this should not come. So C has to be 0. That is the key observation. And therefore, y of s is 2 by s cube minus 1 by s. And therefore, y of t is
E square minus t.
t square minus 1. And go back and check. T square minus 1 satisfies all these conditions. You check this. T square minus 1 satisfies this. T square minus 1 satisfies this. And t square minus 1 satisfies this. Okay. So it's such a powerful theory. I hope you share my excitement. Very difficult looking differential equations using all the theory of Laplace transforms, including, you know, the limiting behavior. Including the limiting behavior, you could solve it. And there is a nice equation. Okay, this is my last slide. Our last lecture will be tomorrow. Let me stop sharing. Our last lecture will be tomorrow, and we will have exactly one discussion session in this week. No discussion session tomorrow afternoon. No discussion session Thursday afternoon. Our discussion session will be Thursday 11:35 for D1 D2 together. Okay, so let me stop recording also.